Hello everyone. In today's class, we are going to see the atmospheric topic in flight mechanics. So the basic or the very preliminary topic in flight mechanics is the atmosphere. First of all, why we need to know about atmosphere is the aircraft that we design is not going to fly at a sea level. It is going to fly at a higher altitude than where we live on a day-to-day basis. So we need to know how the atmosphere, what is atmosphere? The air that is surrounded us, not just the one we are living, it's above the altitude as well, right? So as the altitude goes up, how does the atmosphere behave? Which means how does the temperature is going to behave? Is it going to be the same as the sea level, or it's going to increase or decrease? Similarly, how does the pressure is going to behave? It is going to be the same level or increasing or decreasing. If at all it is increasing, how it is increasing. If at all it is decreasing, how it is decreasing. All these things we need to know, including density and all. So all the parameters and its variation with respect to the altitude that we need to study, so that it will be easy for us to design our aircrafts so that it can fly easily and efficiently when it goes at higher altitude during the flights. So that is the reason we need to learn the atmosphere. Okay, it's it's not something like a geoscience or something like that. It is very much required for all the aerospace engineers to understand how your earth is going to change, or how the parameters of the earth, how the climatic conditions of the earth is going to change as you increase your altitude, as you go higher, and how does that is going to affect your design of the aircraft. So that is the reason we need to study the atmosphere. It's not something related to geography or geoscience. Okay. With this introduction, today's class, let's get into the actual definition of atmosphere and how does that varies and all those things. Generally, people think that atmosphere is a very easy topic. Yes, I do agree that it is very easy topic, but there you have to go very deep to understand it completely. Generally, we all study in such a way that okay, we'll study the definition and we study the equations of the atmosphere, how the temperature is varying, how the pressure is varying, how the density is varying. We just memorize that and we'll just come out. That is not the case. When you want to crack competitive exams like GATE, if you just study at that superficial level, it might be very difficult for you to answer all the questions. So in today's class, we are not going to just study atmosphere. As soon as we study atmosphere, we are going to apply these concepts of atmosphere by solving previous year GATE questions problems. Okay, that will help us to appreciate what we have studied, and that will help us to apply what we have studied in the concept. So we are not just going to study the definition of atmosphere or just the equation. We are going to see how these equations has come and under what conditions these equations are going to be valid, and under what conditions it's going to fail. And all these understandings we'll be getting through in the next 30 minutes. Let's start with the definition of the atmosphere. So it is the region of air surrounding the Earth's surface and while goes along with the Earth during the Earth rotation. So it's very simple. It's a plain English sentence. So it's the region of the air that is surrounded by in the Earth, and that air will also move along with the Earth rotation. So that's the reason even though the Earth is rotating, we don't feel any difficulty for breathing and all, because the air is also rotating along with the Earth. Okay, so that part of the region is called atmosphere. It is very simple, right? You go and stand outside a road, that's an atmosphere because air is surrounded by you, right? Or you are surrounded by the air. Okay, but don't restrict your thought process up to the building that you live or up to the streets that you see. No, atmosphere extends all the way from the Earth's surface to 120 kilometers altitude. You see, this is very, very important. 120 kilometers altitude. So beyond that, it is not atmosphere. So this definition will hold true only till the sea level, till the 120-kilometer altitude, not more than that. But Earth will even go beyond that. Okay. So those are called rarefied gas mediums and all those things, where your satellites or the vehicles which launches the satellites and all will travel even beyond 120 kilometers altitude. But the atmosphere is limited only till 120 kilometers. Okay, beyond that it is not called atmosphere. It is called a rarefied gas medium because you will not have a continuous air over there. Okay, so from the sea level or from the surface of the earth till 120 kilometers altitude, the atmosphere will be there. So this is the definition of the atmosphere. Now within this 120 kilometers range, the atmosphere is divided into the following layers, like a troposphere. It extends from 0 to 11 kilometers. Stratosphere, it after 11 kilometer, it is called stratosphere till 25th kilometer. Then the mesosphere will come. Then the exospheres will come, and finally ionosphere will come. After ionosphere, atmosphere will get over. So ionosphere will be close to 120 kilometers. Okay, ionosphere will exist till only 120 kilometers. Beyond that, ionosphere won't exist. So beyond that, atmosphere is also not there. Okay. Now the layer which separates the troposphere and the stratosphere is called tropopause, which means what? The layer that is between the troposphere and stratosphere is called tropopause. So when is the troposphere is getting over? The troposphere is getting over at 11th kilometer, right? Then the troposphere tropopause will be there at 11th kilometer. Okay, that's a layer which separates troposphere and stratosphere. Being an aerospace engineer, we are so much interested towards the troposphere and the lower parts of stratosphere. What do I mean by lower part of stratosphere is it is close to 15 kilometers or 16 kilometers. Okay, right from the sea level, because generally the aircrafts will fly around 15 kilometers, not more than 15 kilometers basically from the sea level. When you talk about in terms of feet, right, it is close to 35,000 feet to 40,000 feet generally, but even smaller aircrafts will fly much lower altitude than the 35,000 feet, maybe 25,000, 30,000 feet also it will fly. So mostly all the commercial aircrafts will fly not more than 40,000 feet altitude, which is close to 15 kilometers altitude or whatever it is. Okay, so being an aerospace engineer, we are so much interested towards the change that is happening in the troposphere and the change that is happening in the stratosphere, because that's where our aircrafts are going to fly, not beyond that. Does it make sense? So we will deep dive into what is troposphere, what is stratosphere, how does the variations are happening in troposphere and stratosphere. Okay. Yep. So moving ahead, this is the atmospheric relationship as you have seen, right? And the temperature will vary, right? You all know that as you go high, the temperature will come down, right? You all know that, right? So this is the variation of temperature. So where T naught is the temperature at the sea level. Sea level is nothing but the the places where we generally live. Not that everybody is living in sea level. Mostly sea level. Chennai is a sea level, where Bangalore is not a sea level. Bangalore is close to some 900 feet above or the sea level. So that's why the Bangalore is slightly colder than the other plains like Chennai. Whereas Himalaya is definitely not a sea level, right? It is much higher altitude than the sea level. So T naught is whatever is mentioned here, right? T naught, P naught, rho naught, all these things are, so naught represents the sea level parameter. Okay, naught represents the sea level parameters. And here, if you see here, the atmospheric relationship, right? So as H is the nothing but the altitude, and 0.0065 is nothing is called lapse rate. Generally, this is called A. It is denoted by A, and this is called lapse rate. Lapse rate is nothing but the rate at which the temperature is dropping. So the unit of lapse rate, okay? So it's the drop in temperature per kilometer. So the unit of lapse rate is degree Celsius per kilometer. Okay, yes. So that's called lapse rate, the rate at which the temperature is coming down for every kilometers. So generally it is denoted as lapse rate A, or 0 point, and the value of that is 0.0065. So now it's very easy, right? So for example, if this is the sea level and a person is standing here, and if this is some at some altitude and aircraft is flying, let's assume that this altitude is 10 kilometers. Let's assume like that. So this altitude is let's put it's 10 kilometers. And if somebody wants to know what is the temperature at the altitude 10 kilometers, it is very easy to calculate using this expression, right? Because T is what you need to calculate. T 10 kilometers is equal to T naught is nothing but sea level temperature. Sea level temperature we all know, which is 288.15 Kelvin minus 0.0065 into the altitude. If you substitute 0.0065, which means that it is not in kilometer, the kilometer is converted into meter. So you have to substitute the height in meters. So 10 kilometers is nothing but 1 kilometer is 1000 meters, 10 kilometers is 10,000 meters. So you have to substitute 10,000 here and you will get the value. What is the altitude? What is the temperature at the 10 kilometer altitude? So 288.15 is nothing but the sea level temperature minus the lapse rate, which is 0.0065 into the height at which you want altitude. So in this case, it is 10 kilometers. So 10 kilometers, if you convert that into meter, it is 10,000. That's it. Okay, fine. And once you get what is your T, then you can also easily calculate what is the pressure at 10 kilometer altitude, what is the density at 10 kilometer altitude, any altitude for that matter. The example that I have taken is 10 kilometers here. For that matter, you can select any altitude. Okay, and G is nothing but gravitational constant, and A is nothing but the lapse rate, 0.0065, right? That is nothing but A. So I'll put 0.0065. G is nothing but gravitational constant, you all know. R is nothing but the gas constant. So R, you know, right? R is equal to 287, whereas G is 9.8 or 9.81. Okay, so like that. Now if you know the temperature at that altitude, then you can substitute that temperature and substitute the sea level temperature, which is nothing but 288.15. And you need to also know the sea level pressure. We all know what is the sea level pressure, right? The standard atmospheric pressure. P naught is equal to 1.01 bar. And rho naught, which is nothing but sea level density, is 1.225 kilogram per meter cube. So these are the pressure and densities of the air at the sea level. So if you substitute that, then you can easily calculate the pressure and density once you know the temperature, right? Then that gives the complete picture of atmosphere parameters changes with respect to the altitude, right? So far so good. Generally people think that okay, this much you study, then the atmosphere is completed and done and you mastered atmosphere. No, that's the wrong assumptions everybody has. There are a lot of more insights that we need to derive from atmosphere. Okay, so when you go for a competitive exams, these kind of knowledge is not sufficient. You have to deep dive into how these equations has come, when this equation is valid, when these equations are not valid, and things like that. So now generally we all study the definition of atmospheres like this and what is different layers, and then we'll see what is the relationship of atmosphere, what is the temperature variation, what is the pressure variation, what is the density variation with respect to the atmosphere. Then you simply finish the concept of atmosphere. No, now let's study the same atmosphere in a different way. Now let's first try to understand that does the equation matches with reality? Let me put this case. So there is a bulb, okay, which is a source of heat and light energy, which has been shown here, right? So this is definitely the source of light and heat energy. So let's assume that it is around 40 watts. And if the bulb is burning, right, which means it's glowing, you cannot go and touch it, right? It will hurt your fingers, which means that what? It is giving lot of heat and light energy. So if you go close to the bulb, you will feel the difficulty, right, of the burning sensation, right? And if you touch it, you'll have a lot of difficulties. But as you go close, you will feel the heat, right? Because the bulb might be somewhere in the ceiling, but once you go close to the bulb, there is a problem. But otherwise, it'll provide you enough light and heat. Does it make sense? So which means what? If there is a source of heat energy, as you go close to that heat energy, you will feel the heat, right? Is everybody is in agreement with that? Any second thought here? Okay. Okay. Now let's put the same scenario in a different case. So let's go here. So sun. Sun is the source of heat and light energy, right? So here there is a sun, and sun is a source of light and heat energy. The previous scenario, the light and heat energy source is the bulb, which was around 40 watts. Now the sun is, let's assume that some million watts it is producing. So through which we are getting the light and heat. And I hope you all know Uti, which is at a higher altitude compared to the sea levels. But Uti is much cooler than the sea level. You all know, right? Not necessarily you have to take Uti. Even you can take Himalayas or anything. But through the logic that we discussed in the previous slide, it is very evident that, right? It is very evident that the place which is very close to the source of the heat energy has to be much hotter than the place which is far away from the source of the heat energy has to be cooler, right? But here in nature, that's not happening, right? Have you noticed here? Sun is here, Ooty or Himalayas, anything which is closer to the sun is cooler than the sea level. The sea level is even away from the sun, which is close to the sea level, where the temperature is higher at the sea level, whereas the temperature is lower at the altitude. It could be Ooty, Himalayas, or anything, right? So there is a difference here, right? Compared to the previous scenario and this scenario. Here you see, as you go close to the heat energy, you'll feel the difficulty to reach, which means the temperature is higher near the bulb. Whereas here, as you go towards the sun, you see the temperature is dropping, right? So have you ever thought about this? Why this is very well related to atmosphere, right? We just saw the equations and everything, right? Have you ever thought about this? What is happening? Where are we not connecting things? So let's see. So we do not connect things, right? I hope you all would have studied a phenomena called black body radiation. Okay. So the physics behind this temperature higher in the sea levels and lower in the altitude is the black body radiation. Let me explain what is black body radiation. Black color or the black wavelength has a unique ability to absorb the heat and it re-emits it. For example, if you wear a black shirt and go outside in a hot sunny day, you will feel much hotter than the other person, your friend or somebody who is wearing a very light shirt, which means that a white color shirt or a very light color shirt. And if he is also walking along with you on a hot sunny day, the heat that he feels is much lower than the heat that you feel, because black color or the black wavelength has a unique ability to absorb heat and re-emits it. So whenever a black is there, right, a black color or black wavelength is there, let's assume that if this is the black color, it will not only absorb the heats, it will absorb the heat and also re-emits it from here. So this black color will become is a source of the heat. That's the reason when you're wearing a black shirt and going out, it not only absorbs the sunlight, but it also started to re-emit after some time. So you'll feel that your body is so hot because this black color initially absorbed all the heat and now it's starting to re-emit it. So you're very, very close to the source of the heat. That's the reason when you wear a black shirt or anything, you'll feel much hotter than a person who is wearing a light color shirt. That's why when you go out, if you wear a very light color, white color shirts, you will not feel that much hot compared to a dark color shirt. Similarly, scientists say that the whole earth itself is a black body. Okay, the whole earth itself is a black body. What do I mean by that? If there is a sea level, right? If this is sea level, if you dig inside the sea level, right? If you dig inside the sea level, right? So this is that inside the earth will be there, right? That will be so hot because the whole earth acts like a black body. It absorbs heat and also re-emits it. That's the reason the land in the earth, which means what? This part. See this part, which not only absorbs heat and it also starts to re-emit after some time. Since the sea levels are very, very close to the land or it just attached with the land, it not only gets the temperature from the sun, but also it gets the temperature from its own land by re-emitting. Whereas that re-emitting will be very less compared to the sea level for a elevated places like Ooty or like Himalayas. So those kind of places, the land area will be very less. Hence, this radiations will be very less. So this black body radiation concept will be very high in the sea levels where the land is there. It absorbs and re-emits the heat. So sea levels will have two sources of heat now. One is from the sun, the other is from its own land. That's why it feels much hotter compared to the hilly regions where the re-emission is very, very less compared to the sea level. Hence, it becomes much colder. Does that answer your question? Yes, right? So, which now makes sense, whatever the equation that we have studied, right? What we have studied, yes, the temperature will get decreased, right? If the sea level temperature is 288, this is T naught. As the H increases, as altitude increases, temperature is going to come down. Right? Yes, because you see there is a negative sign here, which now goes well with the equation. The reality in the world is now goes well with the equation, right? The equation also tells the same thing. As altitude increases, the temperature will drop. So that we understand using the concept, the black body radiation, which makes sense. But the story does not stop here. Okay, there are a lot of things to understand. The first question here is, as I told you here, right? So these are the equations that you have studied. And now we understood the physical part of it. Why the temperature is decreasing? Because of black body radiations. So as you go away from the earth, the radiation effects are very less. Hence, the temperature is less. Then the next question will come. How long I can go like that? So do you think this temperature reduction is valid till you reach sun? No, right? Because as you go close to the sun, you'll be burnt, right? That's what this figure tells that. This, as you go close to the source, you'll feel the heat. Similarly, as you go close to the sun, you will be burnt even long kilometers away. You will not even reach the sun, right? Correct. So now how long you will go like that, and how long this black body radiation effects will play a role, and that will reduce the temperature. So all these questions, and first of all, how did you arrive at this equation? Why it is T naught minus 0.0065? Why it is T naught square minus something? Why it is T naught minus 0.0073? Some different number. How can you reach this number? Why it is 0.0065? And why it is linearly varying, right? So it is, if you compare this equation, it is like, how does it look like? Y is equal to mx plus c, right? Where c is a y-intercept, right? T naught. In this case, c is equal to T naught, and m is nothing but the slope. Slope is here is the lapse rate 0.0065. X is your independent variable, which is h altitude, right? Instead of plus, here minus is there because the temperature is going to drop. So it is as good as a straight line, a linear equation, right? Why it is linearly varying? Who dictated it to vary linearly? And how do we arrive these equations? The pressure and density equation. We need to understand that as well. Okay, so let's now understand that. Temperature equation is a measured quantity. What do I mean by that? It's very simple. What is the temperature equation? T naught, sorry, T is equal to T naught minus 0.0065 H. It is a measured equation. It is not a derived equation. What is measured equation means? People, for every kilometer altitude, they went ahead and measured the temperature manually, experimentally. And then what did they plotted all the points. How did they do? If this is the h-axis altitude, this is the temperature axis. Okay, what is the temperature at say for example sea level might be here. What is the temperature at some 100 meters down might be here, and another 200 meters down might be here, like that they would have plotted all the points, and they would have joined all these points. Then it would have come, then they would have fitted this curve, the line. The slope of that line is 0.0065. That's why it is called lapse rate. And that points, when you join this point, the best fit is the linear fit, which fits like this. Okay, it is a measured equation. It is not a derived equation. Okay, so they measured experimentally, they measured temperature at different altitude, and they plotted it, and they joined all the points, and they fitted the curve, and they found out it to be linearly varying. There might be slight variations here and there because of the climatic changes and because of the different locations of the world. If you go and do this experiment near a North Pole, the temperature values will be different, and if you go and do the same experiment at the South Pole, the temperature values will be different. But on an average, they have done this n number of times and they have reached to this conclusion. That's why it is called International Standard Atmosphere, ISA. Okay, so if you try to derive the temperature equation, you cannot derive it. It is a measured equation. Whereas if I go back, temperature is a measured equation, whereas pressure variation and density variation is not a measured equation. Nobody went to all the altitude and measured what is the pressure and measured what is the temperature. No, because it is difficult to, it might be difficult to measure the pressure and density compared to the temperature. So where they used the physics and the science to derive those equations. So let's see how this has been derived, and let's try to understand that. Who has derived this? Which law governs this equation? Any equation will be governed by a law. So as I told you, this law or this equations is governed by the hydrostatic law. So Pascal has defined that law, right? You all know, right? So Pascal has defined a hydrostatic law. You all would have studied this, right? When there's a pressure of water at any point, how do you get the pressure of the point? So the change in pressure, which is equal to minus rho GdH, and minus stands for the pressure is going to get decrease as you go high in altitude. For example, if a person is standing here inside this water beaker, the pressure will be more because there are a lot of fluid particles, water, that will put pressure on this guy. Now the same person who is coming and standing near here, he will feel less pressure now because the water which are above him is less compared to the same person when he is standing near the bottom. So which means as you increase your altitude, the number of fluid particles, it could be water or it could be air or whatever it is, that is going to be less. So hence the pressure exerted by those particles will also be less. So that's what this negative sign. The change in pressure is purely coming from the change in altitude. So this is the hydrostatic law. You all would have studied this during your school times. So dP is the nothing but the change in pressure, which is equal to minus rho GH dH. So the change in pressure is purely driven by the change in altitude dH. Right now we are going to use this hydrostatic law to find out the relationship between the altitude and the pressure in atmosphere. But the basic difference between the hydrostatic law and the concept that we are applying is, as the name suggests, hydro means water. This is a water law, hydrostatic law. Okay. Now we are going to convert this hydrostatic law into the fluid mechanics world, because fluids is comprised of both gases and liquids. So air is gas. Even though this law is defined by Pascal for hydros, which is for water, now we are going to convert this to air or gas so that it can be suited for the fluid mechanics world as well. Let's see how are we using this hydrostatic law to get these relationships, right? So I told you that temperature relationship is a measured one, whereas pressure and density relationship is not the measured one. That's the derived one. And the law that governs this equation, P by P naught equal to T by T naught whole power G by AR. The law that governs these two equations are the hydrostatic law. And now let's see how we are converting this hydrostatic law into the that is also applicable for the air, which is the fluid mechanics law. So let's start with this. dP is equal to minus rho G dH, right? So now what I have done here, let me write here. dP is equal to minus rho G dH. You all know ideal gas equation, right? What is ideal gas equation? P is equal to rho R T. Now, instead of density, how can I write that? Rho is equal to P by RT. Now instead of rho, I can substitute P by RT from hydrostatic law. That's how this hydrostatic law is now getting applicable for even gases. Air, because this is the ideal gas equation, right? It is not a liquid equation. This is the ideal gas equation. P is equal to rho RT is an ideal gas equation. So what I'm going to do is, what is hydrostatic law says? dP is equal to minus rho GdH. Now dP is equal to, instead of this rho, I'm going to substitute P by RT from the ideal gas equation. So minus P by RT into G into dH. So that's what you are seeing here. Does it make sense? Now the hydrostatic law is the basic law is now slightly converted to gas form as well. Now it's very easy. It's then mathematics. So now what we are doing, we are bringing this P to one side. So you know, right, variable separable method. We need to just integrate it so that we know what is the pressure at different places based on altitude. So I have bring down this P here, minus G by dH by R. Now T is the T at which you are looking at which altitude. So we have already found a T, right? What is T here? T naught minus 0.0065 H. 0.0065 is nothing but A. So instead of t, now we can substitute that equation because t is also a function of h, right? Ultimately, we are going to integrate this with respect to h. The variable here is altitude h. So instead of t, now we have substituted T naught minus AH so that we will get what's the temperature at that particular altitude. And you can consider like this: the sea level might be 1, or like or you can consider 2 points also, that's fine, at any 2 altitude. So integration from 1 to 2, 1 to 2 is nothing but 2 different altitudes. dp by p is equal to minus 1 to 2 g into gh r into T naught minus AH. Okay, so now if you integrate this, 1 by x is integrated by ln. So ln, so if you integrate this, what will you get? I'll do that here. Ln p, the limit is from 1 to 2. Here also g by a is this one, okay? A into r into ln t. Actually, what would have happened here is, you know how to integrate this, right? This is nothing but 1 by this entire term into differentiate this and substitute here. So what is this entire term? How does this value has come? G is constant, so G by R you can take it out. Okay. So ln of T naught minus AH. Then you have to differentiate what is inside here. T naught is a constant and that will become 0. Minus AH, if you differentiate that with respect to H, minus A will come. So minus A, minus will come here, minus A, and already a minus is outside, so that minus, this minus will go out. Hence you will get G by AR ln T, because T naught minus AH is nothing but T. And now here also 1 to 2, if you substitute the limit, ln P2 by P1 equal to G by AR ln T2 by T1, right? And if you're using the power law of logarithms, this will go here. So this has gone to the power. So now if you take anti-log on both the sides, P2 by P1 is equal to T2 by T1, the whole power, G by AR, where G is equal to gas constant, which is 9.81, and A is nothing but lapse rate 0.0065, whereas R is nothing but gas constant 287. If you substitute all these values, right, which is 9.81 divided by A, which is 0.0065, into R, which is 287, you will get the value to be 5.25. So that is a constant number, you can memorize that. So G by AR is nothing but 5.25. Okay, so now you also know the pressure variation with respect to the altitude. So here P naught is the sea level pressure, which is I have told you 1.01 bar, and T naught is the sea level temperature, which is 288.16 Kelvin. So T is the temperature at which altitude you are looking for, that you know how to calculate, right? From the measured equation, T is equal to T naught minus AH. Once you get that T, substitute that T here, then the whole power 5.25 will give you what is the pressure here. So we are not only have got the pressure relationship with respect to the altitude, but we have also got the density relationship. It is very easy, right? You just, instead of P, using the ideal gas equation, what is the ideal gas equation? P is equal to rho RT, right? Instead of this P, substitute rho RT in this left hand side. RT is, so what will you get if you substitute that? P by P naught is equal to T by T naught, the whole power. I'm writing this equation there, G by AR. Now instead of P by P naught, you substitute using the ideal gas equation. What is P? P is equal to rho RT. Then rho RT by rho naught RT T naught equal to T by T naught, the whole power, G by AR. Now R is a constant, it will get cancels each other. So rho by rho naught is equal into T by T naught is equal to T by T naught, the whole power G. So if you take this T by T naught that side, what will you get? Rho by rho naught is equal to T naught by T into T by T naught the whole power G by AR. If you reverse this, what will happen? T by T naught the whole power minus 1, right? So instead of T by T naught whole power minus, then if you sum it up, what will happen? Rho by rho naught is equal to T by T naught the whole power G by AR minus 1, right? So that's what the density variation. So G by AR minus 1 is nothing but, it's very easy, 4.25, because G by AR is 5.25, G by AR minus 1 is 4.25, which means what? The pressure and density are varying non-linearly. You see, the whole power 5.25 and 4.25, whereas the temperature is varying linearly. If you see here, yes, see this equation, temperature is just a linear line, y is equal to mx plus c, whereas pressure and density is non-linearly because G by R is equal to 5.25, G by R minus 1 is equal to 4.25. Does it make sense? Good. So you also know how to derive it. So what is the basic law that governs this equation? Is the hydrostatic law defined by Pascal. Okay. Now if you see here, let's also understand how the variation is happening, which means what? It is very clear that temperature is going to vary linearly, which means the temperature is going to drop linearly. As the altitude increases, the temperature is going to drop linearly. Now let's understand how does the dropping will happen between pressure and density. Whether pressure drops much faster or density drops much faster, which is going to much steeperly dropping down. So that's part we need to understand. So that part let's understand from the graph that is shown here. What is this graph? The x-axis is the altitude. So as the altitude increases, it will move from the positive x-axis side. You see, from this is 0 here, 5,000, 10,000 feet. It is given in terms of feet. There are two y-axis here. The first y-axis is the pressure one, which is here, left hand side, and the right hand side is the density. The blue line corresponds to the pressure line, which is the first y-axis, which is the left hand y-axis, and the pink line or the rose line that corresponds to the second y-axis, which is the density line. If you see here, obviously the pressure is dropping much faster than the density. The pressure drops much steeper than the density. The reason is, it's very evident that, right? 5.25, here it is 4.25. So the drop in pressure is much faster than the drop in density. Both of them drops non-linearly, that is very evident here. But who is dropping very fast? Who is dropping very faster? Pressure. If you, for example, if you travel from 10,000 feet to 11,000 feet, you will feel the pressure difference very pronouncingly than the density difference. Does it make sense? And that is, numerical is also going very well because 5.25, because T by T naught will be less than 1. Okay, because T will be always less. T is nothing but the temperature at altitude. T naught is the sea level temperature. Sea level temperatures will always be greater than the temperature at the altitude. So T by T naught will be always less than 1. Right? It will be point something. Whole power 5.2. So this whole term will come down. Okay. So that's the reason. Whereas in this, all the equation that we have studied till now is only valid in troposphere. You know why? That pressure equation that we have derived, the density equation that we have derived is from the temperature equation, right? The measured equation, T is equal to T naught minus AH. That T is equal to T naught minus AH, if you remember, what did I say to you? It is a measured equation. It is the experimental equation. That is only done in troposphere. Nobody flew all the way till stratosphere and measured that. But in stratosphere, the temperature does not even change. It is a constant temperature. That's why you see the right hand chart now. Here now the x-axis is just the same. First y-axis is also the pressure axis. Now the second y-axis, the pink line is the temperature line. Here it is density. In the second plot, it is temperature. That's why to see the temperature is varying linearly. Now you see it is varying linearly. But this is the point where tropopause comes. I told you, right? 11-kilometer altitude is nothing but tropopause. That 11 kilometers altitude is close to 35,000 feet, close to that. From there, if you see, it is very constant till stratosphere. So stratosphere is somewhere between 80 to 90,000 feet, which is close to 85,000 feet. After stratosphere, the temperature is going to increase. After stratosphere, the temperature is going to increase. That's why you see the pink line is again shooting up. This validates well with the black body radiation phenomena, right? The black body radiation phenomena will hold true till troposphere. After that, it is just constant. Even though the altitude is increases, temperature is not increasing, neither decreasing. After that, what is happening? It is going close to the sun. The altitude is going close to the sun. So the temperature is started to increase. And as you reach further altitude, as you go further, the temperature will shoot up like anything. And you cannot even reach near to the sun. Does it make sense? Now the whole picture is given, right? Now you would have got the whole picture, right? Excellent. So pressure and density varies non-linearly, whereas temperature varies linearly, and the pressure drops much faster in troposphere compared to density, whereas in stratosphere both will drop in the same variation, both your pressure and this is very important line. Don't miss this line. Pressure and density drops in the very same variation because temperature is equal to constant, right? Temperature is not T0 minus 0.0065 H. Temperature is just whatever the value at 11 kilometer, that is going to be the constant. So in the entire stratosphere, entire this region, the temperature is the temperature at the 11-kilometer altitude. That is going to be just the same till 25-kilometer altitude, which is 85,000 feet. So if the temperature is not varying, then how we derived the pressure and density variation using this temperature variation, right? If the temperature is going to be constant, then obviously the variation of pressure and temperature will also be just the same. So within troposphere, pressure will vary much faster than temperature, than density, whereas after troposphere, in the stratosphere, since the temperature is constant, the pressure and density will vary in the same fashion. The pressure and density will vary in the same fashion. There won't be any change. This is how you have to learn atmosphere so that you'll have a thorough understanding of everything. Now let's solve one or two previous gate question problems to understand and appreciate these concepts. This is one of the questions which is asked in GATE 2015, if I'm not wrong. So what they have given is consider the density and altitude at the base of the isothermal layer in the standard atmosphere to be ρ1 and h1 respectively. The density variation with altitude in that layer is governed by. So they are asking how does the density variation with respect to altitude? What is that expression? So we already know the expression of density with respect to altitude, right? It's here. Rho by rho naught equal to T by T naught a whole power 4.25. So can we write that directly? No, because this density variation that we have studied is only for troposphere. But what is asked in the question? At the base of the isothermal layer. What is isothermo means? Constant temperature. Isothermal means constant temperature. I just told you what is constant temperature region? Stratosphere. In this region, stratosphere, these equation will not hold true. These equation will not hold true. In this stratosphere region, these equations will not hold true. because this equation has been derived assuming that temperature is a function of height, altitude, whereas in stratosphere temperature will not be a function of altitude. So it's very simple. What we are going to do now is we know what is the basic law that governs this equation, right? We'll start from that. We'll get the answer very easily, right? So let's start from that. So what is hydrostatic law? Change in temperature, dP is equal to minus rho g dH. Here we wanted to calculate the density variation, not the pressure. So using the ideal gas equation, d instead of pressure we can write rho RT, right? Because ideal gas equation is P is equal to rho RT. So now instead of pressure I'm going to write by rho RT is equal to minus rho g dH. Since it is an isothermal region, which is the stratosphere region, temperature is not going to get changed. It is constant. If it's a troposphere, you cannot treat temperature as constant. You have to write T is equal to T naught minus AH. But since it is stratosphere, you are free to take that RT outside because R and T are constant. D rho is equal to minus rho G dH. Now R T d rho is equal to minus rho G dH. Now what we can do? We can do a small integrations. D rho by rho is equal to minus G by RT into dH. Right? So here G by RT is constant. Right? It's very straightforward, that is constant. So what we are going to do is, if we integrate this, right, from, they have clearly told the base it is 1 and the unknown places just they asked for the variation. So you can put like this, if the base is 1 you can put 1 here, and the unknown place right now I'm keeping it 2. Finally when we write the expression we'll make just as P or rho, whatever it is. Similarly if we do that, 1 to 2 ln rho 2 by rho 1, if we integrate this, right, integrate and substitute the limit, which is equal to minus G by RT H2 minus H1, right? But log is there. If you go and see this equation there is no log. It is in the form of expansions, exponentials. So let's take exponential on both sides. Ln and exponential are opposite functions, so they cancel each other. So rho 2 by rho 1 is equal to e power minus G by RT into H2 minus H1. So instead of rho 2 and H2 we can make as rho, because they are asked, if you see the question, the density variation with altitude, rho versus H only they asked. That's why it's see rho and H is given. Rho 1 and H1 are isothermal things. Okay, consider the density of isothermal layer in the standard atmosphere. So that is isothermal layer means base of the isothermal is nothing but the tropopause, which is 11 km. They have to just told rho 1 H1 are that altitude and density. So now rho by rho 1 is equal to e power minus G by RT into H minus H1. So let's compare the answer now. Yes, option A is the right answer. If you don't study atmospheric in the way that we just saw, it will be difficult for you to solve this problem. If you just memorize the equation and go, okay, T is equal to T naught minus AH, P by P naught is equal to T by T naught the whole power G by AR. If you just memorize and go, it will be very difficult. But I also wanted to give you one more hint for this problem. If instead of this, if they asked what is a pressure variation, the answer is just the same. You know why? We just studied, right? Both pressure and density drops in the same way in the stratosphere. Because the question is asked in isothermal region, if you know what is the variation of a density in the stratosphere region, the same variation will hold for the pressure also, or if you know the pressure variation, the same variation will hold for the density, but only in stratosphere region, not in troposphere region, because stratosphere density is, sorry, temperature is constant. Hence you took this temperature out very easily, otherwise it is not possible. Okay, so let's see one more question. This is a very easy question. Which of the following statement is true as the altitude increases in stratosphere of international standard atmosphere? So stratosphere, they asked in the ISA, in the stratosphere, which of the following statement is true? Stratosphere temperature remains constant. If you see, option A is not right because it says temperature increases. Option B says temperature remains constant. Option C says temperature decreases, so that is also not correct. So it's between option B or D. Both of them says temperature remains constant. Let's look at the second thing. Pressure increases whereas density decreases. Pressure will never increases as altitude goes, whether it is troposphere or stratosphere, whatever it is, pressure will always keep coming down. That is by the hydrostatic law. I told you, right? There is a beaker. As you go in altitude, the pressure is going to come down. So option B is also not the right answer because pressure will not increase, pressure will decrease. Whereas density will also decrease in the stratosphere, right? That's what we have seen. The last question also we just derived that it's going to. If you see this graph also, the density and pressure will be the same graph. Okay, this blue line, even though it is shown only for pressure, even for density also it's the same line. It will overlap on that in the stratosphere, not in the troposphere. After this part, from here to here, the blue line and the density line will be the same. Troposphere it is different. That's why you see here it's a troposphere. Does it make sense? Yes. So option D is the right answer. Remains constant. So let's see one more question. It's a very straightforward question. What is asked here is, so they have given, assuming an international standard atmosphere, the sea level conditions are given, which is all not condition. So if you see here, this is T naught, this is rho naught, and this is G, this is R, everything is given. Now they're asking what is the density? The density of air at Leh, you know, right? Leh Ladakh, which is at an altitude of 3,500 meter from the sea level. So they are given altitude is equal to 3,500 meter, and they're given all the T naught, rho naught, all conditions, they have constants they are given. They're asking what is the temperature, what is the density at this altitude 3,500, which is Leh. So you know the density variation, right? So, but this is well within the troposphere. Troposphere will hold till 11,000 meters, but it is well within troposphere. So troposphere equations are valid here, right? So we have studied that, right? Rho by rho naught is equal to T by T naught, the whole power, G by AR minus 1, which is nothing but 4.25. So what is rho here? That's what we are going to find out. Rho naught is already given 1.225, which is equal to T. T is nothing but what? Temperature at that altitude, 3005. So we know the expression for it. T naught minus AH. AH is what? 0.0065. H is 3,500 meters, right? Even though it is, if it is given in kilometers, right, you have to convert it to meter and write it because this lapse rate is in terms of meters. Okay. Divided by T naught, the whole power 4.25. So now it's very simple. Rho by 1.225 is equal to this T minus T naught. You know what is T naught, right? 288.16. If you substitute 288.16 minus 0.0065 into 3,500, that will give you the temperature at that altitude. So that's the first thing we need to know. And that will be close to 265 something. Okay. So if you do that calculation, it is a very straightforward thing. So that will come close to 265. So divided by T naught is 288.16, the whole power 4.25. And if you do this squaring and if you multiply that with 1.225, you will get your density to be 0.86 something, 86 kilogram per meter cube. That's it. So the answer is also simple. So these are the different questions that has been asked in GATE in the previous exam. But unless you study atmospheric like the way we have just seen, it might be very difficult to solve all this question. Don't just memorize this equation and don't just memorize the definition of atmosphere and different layers of atmosphere and go. In that case, you cannot be able to solve these kind of problems. Lot of informations in troposphere. Pressure and density varies differently, and pressure varies much steeper than density, drops much steeper than density, whereas temperature varies linearly. In stratosphere, temperature will be constant, whereas density and pressure will vary in the same variation because temperature is constant. And the law that governs all this equation is hydrostatic law that we have seen so far, right? Yes. And how we have converted the hydrostatic law into gas way through the ideal gas equation, things like that. So with this, the atmospheric topic is covered. Let's see some other topic in the next class. Thank you.
If you like this video, please like, share and subscribe my channel to encourage me. Thank you.